At Qualcomm Technologies, we are pioneering the future of wireless communications as we expand 5G into new use cases and deployments. Our work in cellular positioning started a few decades ago, and last year we showcased our OTA prototypes for wide area positioning. This year, we are continuing to push the technology boundary to enable enhanced positioning services. In this video, we'll showcase how we are taking positioning into the mmWave spectrum as well as supporting improved performance for narrowband IoT devices.
For data communications, 5G mmWave unlocks extreme network capacity and takes user experiences to new heights. On the other hand, mmWave can also support new classes of non-data services such as enabling precise cellular positioning. This year, we have implemented positioning capability in our over-the-air test network in San Diego, California to showcase the level of accuracy achievable in a mmWave network. Here is our mmWave test network setup, which operates in the 28 GHz band. There are 4 transmission and reception points that cover the hotspot deployment. In this test, we have a 5G NR mobile test device based on the Snapdragon 5G modem-RF system that moves along the courtyard. In this demo, we are utilizing a multi-TRP downlink AOD positioning approach, where the device measures and estimates the angle of departure of the reference signals sent from the transmission points. The numbers in the user interface mark the different locations where we took positioning measurements of the device. Let's select a location. We now see the KPIs associated with the measurements in comparison with the ground truth. The dark blue dot in the middle of the circle is the actual device location. The lighter blue dots are the positioning error, and the red circle marks the error threshold in the XY plane. Cycling through the different measured locations, we can see the average positioning accuracies are in the meter range. In addition to this OTA prototype, we have also simulated 5G mmWave positioning performance with various techniques under a wide range of locations and conditions, such as for an indoor factory as well as a city level macro deployment, which showed comparable performance under similar assumptions. In conclusion, 5G mmWave can deliver precise positioning for diverse use cases and deployments.
While we exploit the wide bandwidth nature of 5G to achieve high positioning accuracy, many 5G IoT devices will operate more efficiently with lower bandwidth, like wearables and industrial sensors. With 20 MHz or 5 MHz 5G NR Lite, pure timing-based techniques do not work as well, since the narrow bandwidth reduces time domain resolution and network synchronization errors lead to less accurate positioning. To deliver improved positioning accuracy for narrowband devices, a device-based positioning technique like multi-cell downlink angles of departure can be utilized. Based on the positioning reference signals sent from the G node B, the device can estimate the angle of departure based on relative differences in beam RSRP or received signal strength, which is not sensitive to the reduced bandwidth. With multiple downlink AOD measurements, the position of the device can be determined. Our system simulation utilizes an urban micro model with 57 cells operating in the 4 GHz band. For each of the G node Bs, we assumed a massive MIMO implementation of 256 antenna elements with 64 digital ports. On the device side, we assumed low complexity IoT sensors with a single antenna. In the first scenario, we have 5 MHz narrowband devices utilizing a timing-based positioning technique, downlink TDOA. Positioning accuracy gets impacted by the reduced time resolution and network synchronization errors. We then switch the positioning methodology to a multi-cell downlink AOD, and our simulations show the accuracy improves significantly compared to the previous case. In conclusion, multi-cell downlink AOD is a positioning solution that can deliver accurate, low power and wide area positioning for a massive number of low complexity 5G IoT devices over 5 MHz channels with asynchronous base stations.